Hi, welcome to R&AC Academy. My name is Ram Prasad. Let me give a small brief about me. I did my masters in R&AC and then I worked for 25 years with the various organizations involving in product development and technology innovation functions. I had 5 patents filed on my name. Out of my passion, I transitioned into teaching. Presently, I am into coaching GATE and IES aspirants on R&AC subject. I also conduct workshop on R&AC systems, faculty development programs, etc. for the engineering colleges. Recently, I conducted webinars for the members of ISHRE and ASHRE. Coming to this program, I am presenting here with a series of lectures on refrigeration systems for the benefit of the students and professionals. I believe these lectures will be of great help and learning to all of you. This is the third lecture in the series of lectures on refrigeration systems. We will be discussing various refrigeration cycles and systems. However, I am confining this lecture only to carnot refrigeration cycle and vapor compression refrigeration cycle. The remaining will be discussed in the subsequent lectures. Let me start with carnot refrigeration cycle. It consists of 2 isentropic processes and 2 isothermal processes. Isentropic processes are used for work interactions, namely compression and expansion. Isothermal processes are used for heat interactions, namely heat addition and heat rejection. Next is Carnot theorem. Of all the refrigeration cycles working between a given temperature limits, none can have the COP higher than the Carnot refrigeration cycle. As an engineer, we always search for the best refrigeration cycle, and the Carnot theorem is putting an end to that search. The Carnot COP for a refrigeration cycle can be computed using the operating temperatures, and it does not depend on the working fluid. The most important note point here is that while computing the Carnot COP, the temperatures must be in Kelvin scale only. Otherwise, the COP value does not mean anything. Based on Carnot theorem, the Carnot refrigeration cycle gives us the best performance. But then, is there any refrigeration system in the market that is working with Carnot refrigeration cycle? The answer is no. Why? Due to certain processes involved in Carnot refrigeration cycle, making of a physical refrigeration system is not possible. Well, when did we come to know about this? More than 100 years back. Then, why are we studying the Carnot refrigeration cycle even today? A very valid and logical question. Let me explain this using a small situation. Let us say we are a refrigerator manufacturing company. A person comes to us with a claim. He says that he designed a refrigerator which, while working between 0 and 30 degrees centigrade, can give a COP of 12. He proposes us to buy his design by paying him some royalty. Thereby we can enjoy the complete rights on it. There is nothing wrong with the proposal, but no proposal can be accepted on its face value. We need to take his prototype model to the lab for testing and confirmation purposes. However, what is the guarantee that his claim is a genuine one? If not, the time and resources of our organization will get wasted. That's not a good thing to do. But then, do we have any preliminary checkpoints before we go for lab testing? Carnot COP is the answer to that question. And we can compute it using operating temperatures. In this case, it turns out to be 9.1. Here comes a very interesting observation. The claimed COP 12 is more than the Carnot COP. Hence, this claim is invalid. We are making this conclusion without moving from our place, and this conclusion will not be questioned by anybody, anywhere in the world. That is the power of Carnot theorem. Thermal engineers use Carnot theorem, Carnot cycles, etc. to make a very high level assessment of their new ideas on engines, refrigeration cycles, etc. I hope this discussion helped you to appreciate the importance of Carnot cycle, Carnot theorem, etc. But then, the need of refrigeration for the market, for the society is real. There is no doubt about that. A professional, including an engineer, always perceives a problem as an opportunity to perform. And same thing happened in this case also. Engineers started devising or developing new cycles to meet the refrigeration needs of the market, of the society. And the most prominent, most popular among those new cycles is vapor compression refrigeration cycle. It consists of an isentropic process for compression, isobaric process for heat rejection, isenthalpic process for expansion, and finally an isobaric process for heat absorption or producing refrigeration effect. Let us now discuss the vapor compression refrigeration system. Refrigeration can be produced using VCR cycle by connecting four basic parts, namely compressor, condenser, expansion device and evaporator in a closed loop. Let us first pick up those four basic parts: compressor, condenser, expansion device and the evaporator. And let us now connect them. Evaporator out is connected to the compressor in and it is called suction line. Compressor out is connected to condenser in and it is called discharge line. Condenser out is connected to expansion device and it is called liquid line. Expansion device out is connected to the evaporator in. We had discussed in the earlier lectures that there are four basic functions that are need to be performed by any mechanical refrigeration system in order to produce the refrigeration effect. Let us now map those four basic functions among these four components. Needless to say, compressor performs the function of compression and expansion device performs the function of expansion. Condenser performs the heat rejection function and evaporator performs the function of heat absorption or producing refrigeration effect. Let us now map the four processes of VCR cycle to these four components. Compressor follows isentropic process, condenser follows constant pressure process, expansion device follows isenthalpic process, evaporator follows constant pressure process. That means the evaporator and the condenser will be performing their respective functions keeping their pressure constant. If we name them, the pressure at which evaporator is operating is called evaporating pressure PE and that of condenser is condensing pressure PC. Where all PE prevails in the refrigeration system? At the evaporator, suction line, compressor suction manifold and expansion device out. The portions where PE is prevailing are called low pressure side of the system. And where all pressure PC prevails, the compressor discharge manifold, discharge line, condenser, liquid line and expansion device entry. The portions with PC is known as high pressure side of the system. Okay, with this lecture ends, and if you have any questions, queries, etc., please feel free to write to me. The next topic in this series is on performance computations for VCR cycle. See you then. Thank you very much.